All right, well, today we are going to do Chapter 11, Radioactivity. When you say radioactivity, it conjures up different things to different people. This is the nuclear power plant in Japan that suffered through an earthquake and a tsunami, um, melted down. It was ugly, still is. Thing that's notable to me about this is you see all these little houses around. Things are so congested in Japan that people actually build right next to a nuclear power plant. Can't quite do that here. When the fire went out, people were allowed to come back to their homes. And a few months later, when it was springtime, the gardens in these homes started to produce stuff. The radioactivity is relatively high, and some of the things that popped up out of the ground, kind of like a double ear of corn, these are tomatoes. My favorite, of course, is this, the shark seagull. Okay, that's Photoshop. But the others,
Okay, let's say there's no
the
way.
others are all.
I'm gonna say there's no way. It's impossible.
Just a quick reminder of what's coming up for the week. On Wednesday, we're going to meet in room D204. Not going to do lab, we're going to do chapter 12. Quiz 2 is online right now. The following Monday, so that's after this Wednesday, the following Monday, E2 review right here. And finally, we're back in 204 on Wednesday for the exam. Any questions? Now, I think I kind of must have screwed up a little bit, setting the release times for tutorials and whatever. And they didn't come on when they were supposed to. Probably my fault. But I put them up, they're working, and since they didn't get up until Saturday evening, I'm gonna leave them up until Tuesday at midnight. And I will turn them on and off manually now. So, also, I mentioned this, the departmental assessment is up. It's 15, not 16. Must be completed before exam 2. Again, more extra credit. Any questions? All right, well, let's go way back to chapter 2. We talked about the notion of atomic symbols, elements. We said that the thing that defines what an element is the number of protons in the nucleus. Carbon has 6 protons. Anything with 6 protons is a carbon. We can show this using the atomic symbol, where we display the mass number, the number of protons in the nucleus, that's the atomic number, and we put them together in a symbol like this. This is the symbol for the element. The mass number is the superscript in front, atomic number, subscript, also in front. We noted back in chapter 2-ish that we could have different forms of carbon that have different mass numbers. We call those isotopes. We're going to deal a lot with isotopes of various elements today. Radioactivity. The first reports of radioactivity came about from a lab that was working on phosphorescence. They used photographic plates. Now, in those days, a photographic plate was a big deal because you had to pour them by hand, sandwiched between glass, whatever. somebody went in the dark room and put a bottle of uranium salt down on a stack of plates. When they developed the plates, they saw the big ugly splotches where the uranium salts were, probably fired a guy, whatever. But everyone was quite puzzled why uranium salts would do this. The answer came from Curie, among others, and they basically said that the uranium salts and their decayed products were emitting things, subatomic particles. They labeled these as alpha, beta, and gamma. Alpha particle had a +2 charge. It has 2 protons, 2 neutrons. It's a helium nucleus. So somehow this big nucleus is breaking apart and emitting this chunk called an alpha particle. Beta particle was puzzling. It had a negative charge, behaved exactly like an electron. In fact, it is an electron. But what's an electron doing in the nucleus? That was the real question. Gamma particles came about when a nucleus was excited for some reason, heated, whatever. Basically, it looks like a very high energy photon. These 3 particles, and this has no charge and no mass, really. These 3 particles have different inherent energies. An alpha particle, you can basically stop with a sheet of paper. Very slow, heavy, whatever. Beta can make it through about a centimeter of lead, 10 centimeters of lead for most gamma particles. So very, very different energies. The way we detect radioactivity classically, this is a 1950s version of a Geiger counter. So the idea is the bomb went off, civil defense came around with the little Geiger counters to tell you, don't stand there, there's radioactive waste. Kind of a stupid idea, but nonetheless. We still use these in the lab. The way they work, you have a chamber, a probe here. It's filled with a low pressure of usually inert gas. You have electronics, a battery, whatever, fairly high voltage, 500 volts. When ionizing radiation makes it inside the chamber here, it will ionize the gas, basically leave a little trail where it passed, and the high voltage will arc from the anode to the cathode. When it does, the little lightning bolt goes to the electronics, and you hear a click. Well, that's kind of neat. It's useful. Nothing like hearing it live, though. This is a bottle of uranium nitrate, depleted. So, according to the government, this is no longer radioactive. This is my own handy little Geiger counter. Everybody should have one. If you listen, you can hear gamma rays from deep space making it right through my hand. Okay. The tube is here on the side. Yep, this is not radioactive. We'll put this away. But that's kind of a neat thing to play with. Everyone should have one. So, where do these particles of ionizing radiation come from? Let's start with the alpha particle. Alpha particle, we said, was a helium nucleus, charge of 2, mass of 4. Basically, it comes about when a nucleus, gets upset with itself. The blues here are neutrons, red are protons. We are going to lose 2 protons and 2 neutrons from this nucleus. That's our alpha particle. Now note, when we did that, we started off with 12 and 12. When we lost this, we lost 2 neutrons and 2 protons. So that means the atomic number will decrease by 2, and the mass number will decrease by 4, for whatever nuclei we start with. An example, uranium-238, which we just had in the little jar, can lose an alpha particle. We'll show that as a helium nucleus. Atomic number of 2, mass number of 4. When the uranium loses this, the atomic number of what's left is going to drop from 92 down to 90. We've lost 2 protons. The mass number will drop from 238 minus 4. Oh wait, let's figure out what we formed. We started here at uranium. We're going to drop down 2 atomic numbers. That brings us here to thorium, TH. All right, the mass number, 238 minus 4, 234. So uranium has now changed into thorium, 234. Any questions? This is called a nuclear equation. Nuclear equation doesn't balance the way a chemical equation does. But if you note, the mass numbers must add up on the same side. The atomic numbers must be the same on both sides. Any questions? Let's do a quick problem. If we have thorium-230, it will lose an alpha particle. Let's write the nuclear equation and show what we made. All right, here's our thorium. It's going to lose the alpha. 90 minus 2 is going to give us 88. So we're starting here at thorium. Now it's in the actinide series. So actually on the table it slips in here after actinium. When we go down to 88, we are here at radium. The mass number 230 minus 4, 226. We have made radium 226. Any questions? Let's do another. If we have polonium-214, it undergoes loss of an alpha particle. The nuclear equation. Well, we're going to start with polonium. We are going to lose the alpha particle. Atomic number will drop from 84 minus 2 to 82. So we're here at polonium. We're dropping down to 82. That's lead. So our element here is lead. Atomic number has gone from, mass number from 214 minus 4 to 210. Any questions? All right, well, it's fairly easy to imagine the loss of an alpha particle. Unstable nucleus, a chunk flies off. Beta particle is a little bit of magic. Like I said, what's an electron doing in the nucleus? Well, the beta particle is an electron that's formed when a neutron decides it's already being neutral. It's going to lose its negative charge, which it must have somewhere. And when it does, it's left as a proton. So a neutron changes into a proton and an electron. Here's our representative nucleus again. We are going to take one of these neutrons. We are going to lose the negative charge and convert it into a proton. What happens is the atomic number increases by 1, because we have this new proton, and the number of neutrons drops by 1. The mass number, however, is the same, because they weigh the same. The atomic number increases by 1. So an example, if we take thorium-234, we can lose a beta particle. So one of the neutrons will get lost. The atomic number will increase by 1, up to 91. So we're here at thorium. We are going to go up to 91 for atomic number. That's a big. Pa is a symbol. The mass number does not change, so it stays at 234. Now, what do we show for our beta particle? Well, the mass number is going to be 0, and we can put a beta in. But how about the atomic number? What's the atomic number of an electron? It's not 0, because in order to balance the nuclear equation here, the number of protons must add up on both sides. So instead of 0, this must be shown as minus 1. This is our beta particle. Let's do a couple. Bismuth, 210, uses a beta particle. Let's do the nuclear equation. There's bismuth, 210. There's our beta particle. Now, the atomic number here must be 1 more than we started with here. So that's 84. We look around, we find bismuth. 84 is polonium. The mass number does not change. It's polonium-210. Any question? Well, polonium-210 is an interesting nuclei. It's an alpha emitter. But the alpha particle that it emits is extremely energetic. For an alpha particle, it is the most energetic. If we start with polonium-210, and we lose our alpha particle, the atomic number will drop by 2, giving us 82. 82 is lead. We go from 210 here down to 206. All right. said, this alpha particle is extremely toxic. It takes 50 nanograms of polonium-210 to kill you. No question about it, kills you. This polonium-210, the only country in the world that makes it is Russia. I'm not sure what they use it for, but one thing, we actually buy 8 grams of polonium-210 from the Russians every year. I'm not sure what we use it for. One thing they use it for, though, the KGB uses it to poison people they don't care for. The classic was a Russian spy in London. They were afraid he was going to compromise them, so they invited him to tea. They slipped a few nanograms of polonium-210 in his tea. 2 weeks later, he's dead. Whatever. 1 gram of polonium-210 is enough to poison 100 million people. And we buy 8 of them a year. I'm not sure why. Not only heavy elements can lose things like beta particles, neon-19 does as well. Neon-19 loses a beta. When it does, this goes from 10 up to 11. 11 in our periodic table is sodium. Again, mass number doesn't change. We have sodium 19. Any questions? All right, how about a gamma? Gamma basically comes when the nucleus gets excited, either by collision, near collision, being heated, whatever. It loses its energy, and when it does, it loses it in the form of a photon, high energy photon, which we call a gamma particle. It has no charge. Nucleus doesn't change. We simply excite it and then allow it to lose its energy. Kind of like the flame test, if you will. Again, some gammas are very, very energetic. We heard a couple hit the little Geiger counter here, straight from outer space. Let's do a set. If we have radon, 226, radium, 226, loses an alpha particle. That means that the atomic number is going to drop from 88 minus 2 to 86. That's radon. The mass number will go from 226 minus 4 to 222, and we have just made radon 222. Chlorine 39 loses a beta particle. When it does, the atomic number will increase from 17 to 18. 18 is here, it's argon. The mass number will not change, so it's argon 39. Lead 214 can lose a beta particle. Atomic number goes from 82 to 83. 83 is here is bismuth. The mass number does not change. And finally, the radon we made can lose an alpha particle. When it does, atomic number drops by 2. We're down to 84. We're at polonium again. The mass number will drop by 4, giving us polonium 218. Any questions? Well, the very last tutorial for the course is this. Nuclear equation. Fairly simple. This is written in an unconventional way. Not sure why I did that. I think somehow the grid would not fit. But anyway, here we have magnesium 26. It's going to lose an alpha particle. Sometimes the alpha particle is shown just with the Greek letter alpha. Usually it's He, the helium nucleus. Either one works. The number of protons will drop by 2. Well, the mass number, I guess, drops by 4. We need a periodic table to see what 10 is. 10 is, neon. So this is neon 22. The one on Blackboard works basically the same way. Well, you noted that we sort of like keep seeing the same sorts of nuclei coming up and down as we decay. There's a little chart that's useful to see this. When we lose a beta particle, the atomic number goes up by 1. When we do an alpha decay, the atomic number will drop by 2. The mass number will drop by 4. Let's just follow along as we decay our friend uranium-238. Again, that's the stuff in the bottle. Drops loses an alpha to form thorium, which loses a beta to get electronium, which loses another beta to give uranium-234, which loses an alpha to get thorium-230. We're down to radium-226, and finally radon-222. Now you may have heard of radon, especially if you're buying or selling a home, because people are very concerned about radon, radioactive radon, accumulating in the basements. In order to sell your home these days, you need to put one of these little detectors in. It will detect the radon, which is a gas, in your basement area. If it's above a certain level, you have to do remediation, cover the walls, put in fans, whatever, because it's a gas. Well, you might wonder where the radon comes from in your basement. Well, it comes from the same place that the uranium came from. Big rocks. Big rocks are crushed up, extracted, uranium is pulled out. Most of it. There's a little bit left. Nonetheless, you have this mountain of rock crushed stuff. Okay? What do you do with a mountain of crushed rock? Well, you make cinder blocks out of it. You take cinder blocks and you build things, right? Underneath all of our drywall here, we have cinder blocks. Cinder blocks emit a very small, slow, but steady amount of radon. So you do have to be concerned about it. We're pretty much sealed up here. UIC, we had the entire building was made from cinder blocks that were not sealed at all. In fact, I could take my little detector, hold it up to the wall in my office, and get a reading, which was always the sleep, because the ventilation never got there. But yeah, that's where it comes from. Crushed rock, cinder block, radon. All right, how long does it take for this to happen? We measure radioactivity decay using what's called a half-life. So if we start off with a certain mass of, say, uranium, we wait until it has decayed so there's only half as much left. The time it takes to do that is our half-life. An example, strontium-90 loses a beta particle to form yttrium-90. The half-life is about almost 30 years. So if we started off with a gram of strontium-90, 30 years later, we would have half a gram. Now, strontium-90 is something that is dear to the heart of people that were born in the 50s and early 60s because it's a component of fallout. During that time, people were figuring out how to make bigger and better bombs, and they exploded them right out in the open. When they did, they picked up huge clouds of this dust, went up in the stratosphere, circled the world, and eventually settled and rained down. Strontium-90 was one of the things in the cloud. Baby teeth. When you're born, you get baby teeth, they fall out, right? Apparently they gathered up hundreds of thousands of baby teeth, measured strontium-90 levels. Children born in '63 had 50 times higher than those born in the '50s. Why? Strontium-90 would fall down. It would be mixed in with the stuff in the ground. Strontium is right below calcium. The two are isoelectronic. Any hole that will hold a calcium, as in a tooth, will hold a strontium. And that's where it came from. Fortunately, our half-life is 30 years, and we're at least 3 or 4 half-lives into it being all gone. Any questions? Half-lives vary a lot. These are like billions of years. These are microseconds. Examples. Uraniums are basically those up in the billions. Thorium is 10 to the 10th years. Plutonium, 24,000 years. Carbon, we'll talk about, it's about 5 to 6. Strontium, polonium, 0.38. Polonium-210 specifically. And iodine, very, very fast, 0.02 years. That's about 8 days. Basically, the shorter the half-life, the more energetic the particle that's emitted. That's why polonium is the most energetic of all the others. Why it's so toxic. Iodine-131 is also quite toxic. It's toxic to people because we all need a little bit of iodine. We use it to make thyroid hormone. Now, the problem with this is that iodine is formed in fairly high concentration in nuclear power plants. Ever heard of 3 Mile Island? It was in '79. It melted down. Again, fairly congested area. Huge clouds of iodine-131 were released. Now that's bad news for everyone that lives close, because you're going to absorb the iodine from the air, go straight to your thyroid, and you'll get thyroid cancer. The solution is fairly simple. They handed out potassium iodide tablets to everybody they could find. That potassium iodide floods your body with iodine. You don't incorporate from the air. So that works. Any questions? All right. This was a real test question. Okay? Cobalt-60, half-life 5.3 years. How much of a 1 milligram sample is remaining after 15.9 years? Well, there's an equation for that. I wouldn't bother taking a picture. We're not going to use this because I am not going to try to explain to everybody how to put this into the calculator. All right, that just doesn't work. If you read the question, though, it's designed so that you can do it in your head. Half-life 5.3 years, 15.9 is 3 of those. So initially we had 1 milligram. After 5.3 years, we'd have half a milligram. Another 5.3, we'd have 0.25. And then finally, after 3.13 milligrams. Okay. This also has a bit of a meaning for Triton. Triton was built in 1964. When it was built, people were a little cavalier with their isotopes. And there were isotopes around. Okay? I came here 12, 13 years ago, and I was looking for a sample of something radioactive to use my little Geiger counter with. I was digging in the stock room in the lab, and I came up with a little sample of cobalt-60. Now, cobalt-60 is an extremely powerful beta emitter. There is no way in the world cobalt-60 should have ever found its way into there, just sitting in an envelope. No. I took my Geiger counter and checked it. It was non-radioactive. That's because the half-life is 5.3 years. After 10 years, we did have just a tiny bit. Doesn't even show. So we're good now. In 1964, I wouldn't have gone in that cabinet. Whatever. All right. Another example of radioactive half-life that is useful. There's a lot of nitrogen in our atmosphere, right? We have a sun. One of the things the sun spits at us constantly are high-energy neutrons. Nuclei have the ability to absorb a neutron as it flies by. So nitrogen-14 can pick up one of these neutrons from the sun to form nitrogen-15. Now, nitrogen-15 is an unstable nucleus, and it's going to break apart. It breaks apart very quickly, spits out a proton, and makes carbon-14. Carbon-14, we saw, had a half-life of roughly 5,700 years. That makes it very useful for radioactive carbon dating. The way that works, Again, 5,700 years, carbon-14 loses a beta and forms nitrogen-14 again. Now, it does this with a half-life, like I said, of 5,700 years. So pretend that you're alive, and you're breathing and you're eating and whatever. Our atmosphere contains CO2 that has a certain fraction of carbon-14 in it. So as long as you're alive, eating and breathing, the ratio of C14 to C12 will be constant in your body. But when you die, the accumulation stops, but C14 continues to decay. So, you're a saber-toothed tiger. You're walking around, you're breathing, you're eating, just having a good time. You have a certain ratio of C14 to 12. Then, unfortunately, you die. 5,000 years later, you have half as much C14. Another 5,000, 25, 12 and a half, etc., etc., etc. By measuring the ratio of C14 to C12 in a sample, you can tell exactly when the living sample died. That's very useful. Any questions? All right, well, you think that the beta particle coming from a neutron was strange, and it is. Neutron breaking apart to give a proton and an electron. There's one that's even stranger, and that gives us what we call a positron. In a positron, a proton gets tired of being positive, spits out its positive charge, and it forms a neutron. The positron is a positive electron. The process looks something like this. Here we have 13 protons, 11 neutrons. And to take one of these protons, we're going to convert it to a neutron by losing our positive charge as a positive electron. Positron. Now, a positron is our equation. Carbon-11 is an example of an isotope that does this. Forms boron 11. Note that our charge here is now +1 because our proton still has the same mass as the neutron. But in order to balance the equation, we must have an atomic number of 1 on both sides. Now, positron is an example of antimatter. You may have heard of antimatter if you watched Star Trek. Yes. And they were right. Scotty was very careful never to let the antimatter and matter mix. Because if they did, you would get total annihilation. Well, that's true, actually. Matter and antimatter, if they combine, annihilate each other. What they do is they form gamma particles. Now, the gamma particles that are formed when the positron hits an electron are not just randomly released. They are released from the electron in opposite directions. Fairly high energy, opposite directions. 180 degrees exactly. Somebody figured out that this would be a great diagnostic tool and came up with the concept of positron emission tomography, a PET scan. In a PET scan, you're going to take an isotope that releases a positron. Typically, you incorporate it in a sugar. Sugars are selectively absorbed by tumors. So after a little bit, you accumulate this inside your tumor. So let's pretend that you have a tumor in your head. Okay? Fluorine-19 accumulates, fluorine-18 accumulates. The beta particle, the positron encounters an electron. We form two gamma particles 180 degrees apart. So this happens right there where the tumor is. You have a ring of Geiger counters surrounding your head. The computer recognizes that we had a hit here and a hit here at the same time. It remembers the point. Another one happens, and another one. And eventually the computer has enough data to map where they're coming from. And that is a tomography. This is somebody that unfortunately has a very bad abdominal tumor. Shown up very nicely with the PET scan. Again, positron hits the electron, get gamma rays, and you can see it. Kind of cute. Any questions? Well, let's do another little set here with positrons. Acetine, atomic number 33, is going to drop to 32. 32 will start here, goes down to germanium. The mass number will not change. We made germanium 70. Krypton, then lose a krypton 77, then lose a positron. When it does, the atomic number will drop to 35. Mass number will stay the same. We have just made bromine 77. These, we got to figure out where it came from. We're making bromine 79. This plus this is 36. So we look here, try to find 36. We're doing krypton. Krypton 79. Finally, iron 26 plus 1 is 27. This is cobalt. It'll be cobalt 58. Let's just mix them up a little bit. Here's a beta particle. Atomic number will drop by 1. I'm sorry, raised by 1. 17 plus 1. Oops. Okay. Well, argons are given. We could do this. Another beta particle from neon 19. Neon is here. This will go to 11. That's sodium 19. Now look at what's happening here. We're looking for the particle that was emitted. Our number of protons is dropped by 2. Mass number dropped by 4. Clearly, is it alpha? Like this. And finally, Plutonium-239, that's the common stuff that's used in bombs, uses an alpha. This drops by 4, we get uranium-235, which is the other stuff we use in bombs. Now, what makes a nucleus unstable? Basically, it's the neutron to proton ratio. This little black line that kind of goes up like that, that's the line of stability. Things that have too many neutrons tend to be beta emitters. Things that have too many protons go down here, or alpha emitters, so all these guys. And this, the green stuff, this little blue right up in here, those nuclei undergo fission. Now, fission. We've seen an example of fission. We took nitrogen-14, made nitrogen-15. We split out a proton. That's not a big fission, but it's a fission nonetheless. Fission is important to us because the initial hydrogen bombs or atomic bombs are all fission. Okay, an example. If you happen to have uranium-235 laying around, uranium-235 is an unstable enough nucleus that if it picks up a neutron from somewhere, it's a good bad, picks up a neutron, we will get fission. Here's our big nucleus. Kind of ugly. Here comes our neutron, big yellow burst, and we make 3 high-energy neutrons. The yellow burst was energy, about 200 million electron volts worth. That's 2 trillion Kelvin. A lot of energy. Not only that, but we've released these 3 high-energy neutrons that can come back, find another uranium-235, and do it all over again. This sets up what's called a nuclear chain reaction. Nuclear chain reaction is best shown using ping pong balls. Here we have little mouse traps. Each one has 3 ping pong balls delicately placed on top of it. The experiment is to simply drop another ping pong ball on top. This represents the high energy neutron, and it will set off a chain reaction. Kind of cute to watch. Whoosh. Yep. Now, in order to get a nuclear chain reaction to work, you need to have enough uranium-235 around. The amount is called a critical mass. If you have a subcritical mass, you lose the neutrons and nothing happens. So, subcritical mass, neutrons escape. This can either be low density or just not enough of the stuff, not enriched enough. Critical mass, virtually everyone will hit and go with it. Again, ping pong balls. This shows a steady array of these guys represents a critical mass. We drop in another ping pong ball. And we get a nice chain reaction. But if we have a subcritical mass, now this is either low enrichment or low density, we get something like this. You can bounce it, and one ball right down the middle. I probably had to film this 100 times to get it to work, but nonetheless, it's an amazing demonstration. Nuclear power plants. You use control rods, so you have your radioactive stuff down in here. You have enough to form a critical mass. You roll control rods, they absorb the neutrons. Stops the reaction, everything cools down. Pull the control rods up, you hit critical mass again, you get a chain reaction. Really simple. That's for a nuclear power plant. If you're building a bomb, however, you don't want to control the chain reaction at all. You want it to go as fast and furiously as it can. This is a little film clip from the 50s. This is a power system. We're going to shoot an atomic bomb out of the end of this little gun. And then watch what happens. And it goes 3 or 4 miles down into the desert of Nevada. And kaboom. Now when they set things like this off, they position stuff around to measure first the shock wave. And then later blast. Everything is sort back up into the explosion again. And sitting here filming the whole thing. All these guys just filming away. We've got a little all of this nonsense, the yield here was 1 kiloton, 1,000 tons of TNT. Today bombs are 100 to 500 kilotons. Fission bombs. This is a very sophisticated bomb. These are the guys that designed it. You can tell us in a picture. The equipment protectors and the promoters. That's it. That's the whole thing right there. Very sophisticated bomb. The first bomb, however, was not very sophisticated at all. This one was the first one to be used in World War II. It's called a gun-type fission bomb. This is very, very simple. All you need is uranium-235, enough to make a critical mass. You start off with this as a round chunk. This is in a barrel, so it's like a howitzer. You fire this, and you're firing at the target down here, which is the other half of the critical mass. They go together, hit a critical mass, a microsecond later. Microsecond. This was the very first one exploded. about 100 miles from Las Vegas. And this was 13. I'm not kidding. The problem with the gun type bomb is that it's so simple. All you need is a critical mass, cut it in half, hold it together somehow for a microsecond, and it goes. That's it. That's why we worry about people accumulating excess uranium-235, because it's so easy to think about. But nobody makes gun type bombs anymore. Instead, they do an implosion bomb. An implosion bomb uses just a fraction of the stuff that it takes to make a gun type. You typically use plutonium instead of uranium-235. Plutonium you could use for making a reactor, or a beta reactor. The one thing that is tricky about an implosion bomb, your subcritical mass is in the middle. These are explosives that are formed in a ring, a volume surrounding them. And you have wiring so that all of these go off at exactly the same time. That's the critical thing. They must go off at exactly the same time. Because you go in, the force hits the subcritical mass, makes it critical, and you go boom. It increases the density here, so you get the critical. Now the implosion bomb. Well, looks like a soccer ball. About the same size. These are all the shaped charges, hole in the middle for the plutonium pit. Plutonium pit looks like this. It's a little ball with plutonium. These days they have stuff buried inside it. Originally they did. You can hold one in your hand. Here's the shell casing. To make a bomb, you simply take this, put it inside of that, and it's considered a bomb. If this sits on the shelf and this is on the shelf next to it, it's not a bomb. So, there was a treaty for a while as to how many bombs countries could have. Those are assembled bombs. We had like 2,500 assembled bombs. We also had 25,000 of these sitting on the shelf, and 25,000 of these sitting on another shelf. They're not bombs. Okay. Just again. Again, they're small. Just like the one that we saw out of the cannons, this was actually a backpack. Somebody was supposed to wear this, sneak through any of the lines, run to the other side, run back quickly, and it was over. This is a very sophisticated version of it in a briefcase. Russia, well, when the Soviet Union collapsed, there were people guarding their little stockpile of plutonium kits, and these guys. The guards went home because they weren't being paid and it was cold. People came in, swiped these, swiped the pits, there's a whole bunch missing. Technically, the U.S. has lost 11, but that's probably not right. It's probably somewhere between 50 and 100, and who knows where they are. And we were careful. So, fusion. Fusion is the other way to get energy out of atoms. Basically, this is deuterium and tritium, hydrogen isotopes. If you take these and you squeeze them together very, very tightly, you get fusion to make helium, and you get energy. This is the mechanism, basically, that the sun runs by. The sun doesn't use deuterium, it uses protons. Here's hydrogen nuclei. Squeeze these together to make isotopes. Add another one, another isotope, eventually winding up with helium. When stars run out of hydrogen, they start compressing the helium to make heavier atoms, etc., etc. Well, somebody figured out, of course, a way to take that process and make hydrogen bombs. Hydrogen bombs look basically like this. Does this look familiar? That's a fission bomb. You use a fission bomb as a detonator to set off the fusion bomb. So you fire this guy, it releases protons or neutrons, you get a pressure that forces the lithium and deuterium together, and you get an explosion. It is so much more powerful than a fission bomb. Typically they run only 10 to 12 megatons. That was the first one that exploded on this poor little island in the Pacific that nobody will ever go to again. The Russians designed one that was 100 megatons. 100 million tons. They dialed down the power to 50 because they didn't have a plane that would go fast enough to drop it and get away without being destroyed. This was in the desert in Siberia. This is the deepest blast you ever see. They're 50 miles away. This is going 50 miles straight up. Now you might want to ask, why in the world would you need a 50 megaton bomb? Well, it turns out that building the bomb in those days was doable, but that the guidance systems were so bad that you needed a big bomb and just get it close to where you think it. You might recognize this. That's the field museum in the background. This is Lakeshore Drive. These guys here are Nike missiles. On a nice afternoon in the 60s, take your family down and take a stroll through the missile base. There were missile bases all over. Here's Burton Park, Jackson Park, Montrose Harbor, etc., etc. These missiles, the Nike missiles, each contained one of the small kiloton atomic bombs. The idea was the Russians were going to send their big bomb over here to Chicago somewhere. Don't quite know where it would land. As it was coming over the lake, we would start shooting these guys, hoping to get close enough to mess it up. Wasn't a great strategy. nonetheless. We live in Oak Park. When we moved there was a sign up by the Eisenhower declaring it a nuclear weapon-free zone. So we weren't allowed to have those guys in Oak Park. Whatever. The other use for nuclear power is a power plant. Now, most people look at this and think this is a reactor. It's not. The reactor is that little building there. This is just a cooling tower because it gets pretty hot. The idea is you have control rods controlling the core that undergoes fission. It's hot. You have a closed loop system here with water. Pumped over the hot core, comes out. Transferred to another loop system. There's a turbine. Finally, a third closed loop system out to the cooling tower. The idea is that the radioactive water never makes it here. Problem is, however, see those guys? They're pumps. If the pump fails, within just a few seconds, this thing overheats dramatically. The other thing is the control rods. If you very carefully automatically up the lower and up and down, that works. But if something goes wrong, the rod gets stuck, if there's an earthquake, the floor goes away, runs away, melts down on the floor, goes right through the concrete, and you get a classic meltdown. That's what happened in Japan. Again, there was a tsunami and an earthquake. Drenched the thing. Today, Fukushima looks like this. It's covered with water, flooded. Now this water is radioactive. They don't quite know what to do with it. And it's leaking out a little bit. These are the little control rod symbols that are still functioning. So, gentle hue of bluish isn't an artifact of it being underwater. It's actually characteristic of control rods that are in storage underwater. This is the Sirkonov radiation. Again, it's from the neutrons interacting with the water surrounding it. Kind of an eerie looking stuff. The problem with nuclear power is when you're done with these control rods, what do you do with them? Well, nobody quite knew. So what they did was to build giant swimming pools. And they would immerse them in the swimming pool. Swimming pool water got hot, had to pump it outside, cool it off, pump it back. Okay. These are various places around the country that do that. Illinois is here. Illinois leads the entire nation in the number of storage spots. Chicago is right here, Morris is right here, yep, right down there. If something goes wrong in this storage system, there's a total of 9290 metric tons of stuff stored here in Illinois. Now, ComEd gets good money for that, and they're real happy with that. But that's a lot of stuff. Okay? Indiana less is done. So, what do? People knew that the swimming pools were not a great idea. A group at the House of Representatives got together and said, I have an idea. Out in Nevada, we own a mountain called Yucca Mountain. Let's take and build a huge tunnel under this mountain. We'll gather up all the waste from everywhere and bury it. Everyone else looked and said, that sounds like a good idea. And so, they did huge tunnels, put railroad tracks in there, taken way down 1,000 feet underground. They designed these massive transport containers. These contain the radioactive waste. They're hot. Nonetheless, the idea was to take them and put them down here under the mountain. Somehow, they forgot to ask, why is the mountain there? Nobody asked the geologists. Well, where do mountains come from? Basically, you have tectonic plates of crust. When they collide, they tend to buckle up, and you get a mountain. That means that underneath this mountain, it's broken. There's a break in the crust. This type of thing is also called an earthquake zone. The crust is broken. Not only that, but even Nevada has a water table. Where is the water table under this? It's 1,000 feet below. So their idea was to store this stuff on an earthquake fault 1,000 feet above the water table of Nevada, roughly 100 miles from Las Vegas. Fortunately, they said no. Eventually, after building all these tunnels, it's the strangest state or federal park you've ever seen now. But they decided, nope, not going to do it. Too risky. So where's the waste? Still sitting in swimming pools. Most of it in Illinois. As this decays slowly, and remember, it's a billion-year half-life. As it decays slowly, you can take some of it, encase it in concrete, space it out, again in a desert. These are all hot. Or you can just put it in barrels and spread it through the cornfields. Again, I think this is probably staged, but nonetheless, there aren't too many good options, except for fusion. We still need energy, right? Fusion, we said, is the power of the sun. It would allow us to take nuclei, fuse them together, make harmless helium. Good. Problem is, here's the chemistry we would do. Get lots and lots of energy out. But in order to compress these things to the point of doing fusion, you need remarkable machinery. Something like this. There are people, just to put it in scale as to how big this thing actually is. It's designed with this in mind. What you do is you're going to take a gas that if heated to the point, way up there, to the point that it ionizes and forms a plasma. Plasma is charged. If the plasma touches the outside walls, it is so hot, it will melt right through. So, you take the charged plasma, surround this thing with magnets, it compresses it in the middle, and we wind up with plasma in the middle. This is hot, but still you can, it doesn't melt. It's all in a high vacuum or the idea is, you have your plasma being generated, it's hot, closed loop, heat exchanger, closed loop, and a turbine. Problem is, they've been working on that thing for, well, since the 70s. Still hasn't worked. Still takes more energy to get it going than to get out when it's done. There are examples of fusion that have worked. This is the most notable one. These are giant lasers. You put your deuterium tritium pellet right there, fire the lasers, the pressure causes fusion, and you get energy. This is the one, V1, right now, that has actually worked. It got more energy out than it took to fire all the lasers. So that's good. Downside is, had to replace all the lasers because they burned them up. So, doing fusion is not easy. For a while, place called Skunk Works, Lockheed Martin, Skunk Works, top secret, had a device like this. It's roughly 10 feet across. This was a different type of containment than the other fusion. It works. Yes, you got fusion out, but not enough. The hope was this thing could fit on the side of a truck and power a city. Could also power aircraft carriers, whatever. All right. Entity had one also. Both of those they had stopped working on because it just didn't work. That's sad. But hopefully somebody someday will come up with one that does it. Any questions? All right, again, Wednesday, we're in 204 for chapter 12. Quiz 2 is online now. Exam to review is here next Monday, Wednesday in 204 for the exam. Don't forget the assessment, 15 points of extra credit. And finally, today we added one more tutorial, nuclear equation, 350 are your total points, you get the A and no points. All right, I will see you guys Wednesday for chapter 12.
You